semester, tests, assignments, lab reports, whatever else you need to do to sort it out, finish all that off. Then you come back on Saturday, and that topic is just, we're just doing that to prepare for the exam, because the exam has that question there. Okay. Recording? I think so, huh? All right. So where we left off yesterday, so before that, CHE 2161, week 12, lectures on Saturday. Maybe around 9 to 1 with a break. Okay? You can negotiate how long you want to break. The longer you break, then the longer we stretch. Okay? So that you can eat something, not so hungry, not so tired, and so on. Alright. Okay, so yesterday we left off here. Time-dependent behavior of suspension. Okay, so far the one that we did so far was the time independent. Time independent one, we looked at the models. All right, so the fluid can behave whichever way it wants to behave, but we model it, and one possible model is the power law fluid. The other possible model is the Bingham plastics. Okay, so those are the two that we touch on in this unit. There are a lot more. Okay, there are a lot of funny fluids around in this world. Okay, but we only touched on a few. Also, time dependent one, we only touch on a few. Alright. So, sharing time. So these type of fluids, they have like memory, alright, of what has happened before, and they don't have idea of what's going to happen next. That's not possible, but they have a memory of what has happened before, and that may or may not have changed their properties. Alright. Okay. So example, what's actually happening in some of these fluids is if there's a particular structure that it forms. Alright. So if you give it enough time to relax, it will form that structure. So initially it's a bit more stiff. Okay. As you shear it, those structures break down, and then the properties, the viscosity will change. And after, so as you shear it again and again, the properties change. But then if you let it rest again, then you can reform its structure and then be hardened up or stiffen up again. Okay? So that's why it's an example like this. Alright? So initially you let it rest, then you stress. When the stress and release also different. And then you stress and release and so on. So as you see this one, from the shear stress to the shear rate is getting thinner. The viscosity is going down because you're breaking up the whatever structure that is forming up. Alright? And then after that, given enough time to rest, you can start again at number 1. Alright? So this is one of those ones. Okay? Okay. I just said that. Alright, viscoelastic is okay, so it has both parts, the viscous part with the fluid and the elastic part with the solid. So example was Filipati yesterday I played with you. So it also has a time dependent, so when the Filipati also has a time dependent part. If you move fast, it behaves like a solid, it steps off. If you move slowly, it behaves like a liquid. Alright? If you want to play with it, you come to CD tutorial. Fun. Alright? So other examples are like glass, bitumen, and so on. They are not actually solid. Okay, given enough time, they flow. If you go to Europe and holiday, maybe your honeymoon, some few years from now, okay? Few up to you, how many, there's some of you might get married, 5 and 10 and so on. Alright? Or you might go to Europe earlier for other reasons. Some of the old buildings, alright, could be a few hundred years old. Alright? What they notice is the glass at the bottom is thicker than the. Right? When they made the glass, it was uniform thickness, but over time it has flowed down. Okay, and therefore the bottom now is thicker than the top. Alright, that is so glass is not actually solid given enough time and flow, but that needs hundreds of years. Alright, bitumen also the same. It's not actually solid. Given enough time it will flow. Alright. So I think this one, there's a model. Okay. Before I talk this one, I saw the model. So the model, to model this fluid, all right, I just mentioned it, you don't actually do too much about it. Model, so the fluid has two parts. There's a stiffness part, a solid part, and a viscous part, a fluid part. So when you want to deform the fluid, you have to deform two parts here. That's a typical model for viscoelastic fluid, yes, we have. So it's complicated. All right. What we do observe, all right, some of the funny things that we do observe is with viscoelastic fluids is like rock climbing. I think you can look in YouTube. Maybe you'll do that in the tutorial. All right, you can search on YouTube. In normal fluid, if you put a rock in and you swirl it, right, the fluid will tend to circle around, and then because of centrifugal forces, get pushed to the side. Get that one. But for this polymeric fluid, all right, what actually happens is when you put in certain fluids like this, you put a rod in and you swirl it around, actually the fluid attaches to the rod and actually starts climbing. Okay, that's because, so that is the photo, there's another photo. That's because, I'll go down next. Here. All right, the stressor change the fluid property, so it becomes like a solid. And with a solid, it creates a tension like a rubber band wants to bite against the rod. And as he bites and tries to squeeze the rod, that's where the climbing up effect happens up. All right? So you can get funny effect like this. The other funny effect is this one. All right? Normal, initially you start your siphon. Okay, you all know what a siphon is, huh? All right, you stick the tube in. All right, then the tube comes out this side. So in a normal fluid, once you raise the tube above the surface, the siphon should stop. In this case, the siphon will continue, and this is a photo of it. So that's not real. Then the tube starts there. There's this part here where the distributors, right? Because of the stresses again, the fluid is able to form its own tube on the outside and flow on the inside, so that it continues flowing up. Right? It has that ability. Okay, I think explanation. In this case, the elastic nature of the polymeric fluid enables it to extend upwards and be sucked into the tube. Okay, so it starts to show that solid properties there. Okay, this one, there's some analysis of it. I think you don't have to look too hard on it unless you want to. Okay, so this is the model for the Maxwell fluid, the viscoelastic fluid, with relaxation time and so on. Okay. I'll skip all this one. Okay, so this one is the important part. Pipe flow, that's typically in a non-Newtonian question in the exam, 99% of the time it's pipe flow. Okay, not 100%. Also, I forgot to mention, the tutorial questions that we'll do next week, please ignore my one. The one on Moodle looks better. I read it. Where is it? No. Here. Okay, this one, problem set 10 from Moodle. We'll do the same tutorial as our counterparts in Clayton, because my questions are a bit old. Okay, they refresh the questions a little bit. They're still similar, but I think they taken a lot of the partial questions inside. So since our Clayton counterparts are practicing on this one, we're going to practice on this one also. Okay. Rather than practice my one old one, sometimes very difficult. The guy that was teaching it over there, this part, the non-Newtonian, he was here for a while, but then he retired. He came here for last year. Prof. What's his name? Prof. I don't think you guys met him, so never mind. So, Carlos. You met him? Carlos Q. You met him? Some of you older ones have been around. Okay, he was here for 1 year or so, but he was teaching it there in Clayton for a long time. So he is now retired. New person has taken over, so they may have a slight different idea what they want to teach and so on. So with that said, it's better we do the same problem set, then you'll be equally prepared or unprepared, whichever the case may be, for the non-Newtonian section of the exam. Okay? So repeat, ignore my one. So if you printed my one, throw that away. You print out this one here from the